Hi, everyone. I trust you can see my screen. It looks that way to me. So this is, as Anthony mentioned, an update talk. That is, this is really work in progress, not a final product, on a project that I've been working on with a graduate student of mine at UC Irvine on statistical methods for bloodstain pattern analysis. So I have a few slides that I'm going to go through very quickly just to introduce the topic. So bloodstain pattern analysis, if you're here, you probably know something about it, but it takes as its starting point either a direct crime scene evaluation or a careful analysis of photographs from a crime scene that might look something like what you see at the right, and tries to infer from it the stains that you can see and their directionality, what might have happened at the crime scene. So often an investigative tool. There can be multiple objectives. The primary objective is very often to figure out the mechanism that generated the patterns that are visible. And this can be, there's one possible way of thinking about that here into a primary classification, and then within that to secondary type of classification. Other objectives might be to figure out where in the room the event happened, but we're going to focus on this classification task, if you will, or the mechanism determination task. And so this is our examples taken from the game site Sporkle of what different examples might look like. We actually have some data of the ones that appear in red. So you'll see some more pictures of those, a little bit messier to work with than the ones you see in this example. The starting point for us is that it's possible some mechanisms, as you can see here, appear to be easily distinguishable, but some, for example, impact and exploration, may be less so. And in some instances, there might not be a lot of data, and so it might be hard to make the determination. In addition, the determination may depend on characteristics where the bloodstain was. So the standard, as in many pattern disciplines, is expert analysis based on training, knowledge, and experience. And so these end up with subjective opinions based on an examination of the stains and whatever training they had. You may have seen the very recently published report by Austin Hicklin and others, the first, if you will, black box study in which there are examples with known mechanisms causing the stains. And they found they are 11% erroneous responses. And so we are interested here in seeing what one can do with data-based approaches. As I said, it's relatively early stage results and work. The approach that we're going to take is to first try to summarize the bloodstain patterns into some kind of format that will be more amenable to statistical analysis, and then develop some classification approaches based on that data format. So let me begin with the first piece, which has actually been published. So this is just an image processing paper. You can see the reference there, and if you Google the title, you should be able to get it. It has open access. And I should emphasize, this was motivated by our interest in bloodstain pattern analysis, our work here, but this is actually a well-known problem in the scientific literature that applies in other settings. There are a lot of examples in biology where people have images that might contain multiple cells and want to segregate out the different cells. For us, the motivation was an image like the one on the top left here, which is a bloodstain pattern comprised of a lot of individual stains, some of which overlap. And so we've developed a kind of multi-step approach that does some image steps on the first row here. And then our contribution is really going from the third box to the fourth box on the top row through a series of steps that you can see here. And I won't go through them in detail, but we basically come up with a set of potentially thousands of ellipses that may do a good job of summarizing this complicated shape that you see at the bottom here. And so you can get an idea about these many, many ellipses here. And then we just focus on the outline of the stain and then set up an optimization problem to choose a smaller subset, in this case, 4 ellipses, out of the thousands of possibilities that do a good job of summarizing the stain. And so we're imagining, if you will, that this is generated by these four kind of droplets, if you will. We did a large comparison with synthetic data that we generated to two existing methods in the literature. Again, these existing methods were not focused on bloodstains. And the way to look at this picture is actually to start in row 2. That is, we started with this set of randomly generated ellipses, 3 in the first column, 5 in the second column, and so on and so forth. And then we generated the image above it by saying anything that's inside the ellipses is stain. But you can see now, working from just the first row, we apply these 3 algorithms, one in blue, one in red, and ours in green. And we have a bunch of metrics in the paper that suggest the green method, our method, is doing really, really well at this. And here's a bloodstain example where you can see kind of what the difference is. A is the original data, and our method identifies 2 droplets appearing to be on top of each other in the dotted box, whereas these other methods in the literature tend to favor the explanation of a single drop with a slightly unusual shape. So this was our starting point, as I said. It has been published. And what it does for us is, if we're given a pattern is composed of many stains. Each stain, using the approach I just described, can be approximated by a set of ellipses. And each ellipse is really described by 5 summary numbers. The center, the location of the ellipse, so that's an X and a Y coordinate, and then the length of the major axis and the minor axis, and the angle giving its orientation. And so what you see here is a little bit of where we're headed, which is any pattern is summarized by could be a very large matrix where each row is an ellipse, and then you have the 5-number summary of that ellipse. And so here, hypothetically, pattern 1 is impact, and it has N1 ellipses and numerical summaries. Pattern 2, expiration, the same. Pattern M, cast off, the same. And we can have multiple impact patterns, right? And multiple expiration patterns and multiple cast off patterns. Other people have thought of this approach, so we're certainly not the first. Generally speaking, the things that are in the literature have done the following. Number 1, they ignored overlap stains, and that was part of our motivation for the work I just described. Second, they would identify some summary of each ellipse, and I'll show you examples of those, and they would compute a summary for each pattern, saying what's the average size of the ellipse, or where are most of the ellipses located, or things like that. And so then each pattern, and the language here is very important, a pattern is a collection of stains. The pattern basically gets summarized with a set of numbers, and it becomes a standard statistical classification problem. So we're going to do something a little different, but many others have done this. And what I mean by features is they might take the width to length ratio of the ellipse and then compute the average of that across all the ellipses in a pattern. That is a feature. And for any pattern, you might get a number of features. These are 2 papers of the category I just described. The paper on the left came up with these 11 features and then tried to build a statistical classification. The paper on the right did a similar thing. And so here's the distinction between what I'm going to describe in the 10 minutes I have left and what's happened in the past. At the top are the studies I just described. So they have a pattern summarized by a set of ellipses, summarized by a set of features that describe the pattern. And those features go into a classifier. Our method is going to try and do something slightly different, which is to take the same pattern, the same summary of ellipses, but instead of defining features, just say, let's view these 5-number ellipse summaries as a distribution. And so a distribution in 5-dimensional space that characterizes a pattern. And we want to know whether we can work on those patterns without having to pre-specify features. So here's where we're headed. Apologies in advance for math on the next few slides. You don't have to know any of the math. That's primarily for me, and I will try to explain qualitatively what is happening. And so the way to think about this on the left is just notation that says we're going to summarize the data matrix, all of the ellipses with xi. So xi is a distribution, if you will. It's a set of ellipses. And yi is the mechanism. So 0 might be impact, 1 might be expiration, 2 might be cast off. And we have this distribution for a pattern, and we happen to know its mechanism. That's what we're assuming. There are two approaches to analyzing this kind of data statistically. One is what I'll call a discriminative approach or a classification approach. And that is to use the set of distributions that we have with known pattern Y and build a model that distinguishes between these distributions. We're going to use a kernel-based approach. I'll say a little bit more of that on the next slide. The discriminative approach is natural, but I find it a little limiting in that you have to figure out which sets you want to discriminate. And if the truth is not one of them, you'll never get it. An alternative approach is what we call a generative model. And it's an attempt to basically apply likelihood ratio thinking. That is to take a set of patterns from just one mechanism and look at all of the matrices and see if we can describe whether a given matrix is consistent with the matrices we saw from the pattern. So if we have a bunch of impact patterns and then we get an unknown pattern, we want to say, what's the likelihood I'd see a matrix like this if it were an impact pattern? So we have a hypothesis. One quick comment I'm going to make here, when I give this talk to statistical audiences, they always say, well, why aren't you using deep learning, a very powerful machine learning tool that has solved tons and tons of problems? Well, the problem for us, and in many of the forensic applications, is we don't really have a large amount of data, and the data we do have is very inhomogeneous. So that is, you just don't have thousands of cases where you can teach a deep network to recognize a dog from a cat, from a wolf, from a car, from a building. So our data doesn't really fit well in that framework. So these are two pretty mathy slides. Don't want to go into detail, just want to tell you what I'm thinking in terms of the discriminative model. So when you think of a discriminative model, statisticians, you might think about logistic regression. How do I teach a statistical tool to distinguish between two classes based on some set of variables? But that requires figuring out what the right features are, and we didn't want to do that. Kernel-based methods have arisen in machine learning as an alternative to identifying the features. And the way that they work is, instead of defining features, you come up with a kernel, which is a measure of similarity between two, whatever it is you're trying to classify. In our case, it will be a kernel that gives a distance or a similarity between two distributions of ellipses. But more generally, it can be whatever two objects you're trying to classify. And the top picture is really a traditional classification problem representation that says, in a special mathematical setting, if I give you a kernel function, you can identify the features that will optimally do the classification. Our problem is a little more complicated because we just don't have an X and a Y. We have a distribution, right? We have a distribution of ellipses that we're calling X, and then another set of distributions, which is another X, in this case, Y. Okay, so that's, sorry, a very quick description. And this slide, I'm not even going to talk about at all, but it's just one that basically says, if you solve this optimization problem, you can do it, and you don't have to pre-specify anything other than give it the examples and a kernel function. So that's the discriminative approach. I'll come back to some results in a minute. The alternative approach is a generative model. Again, more math here than I like, and I apologize for that. The way to think about the generative model is to really focus in on, whoops, this curved picture here where my cursor is. So this is a one-dimensional version of the world. Suppose I had data that looked like this two-humped curve. You can see for this two-humped curve, I can approximate it by two normal distributions and do a very good job. So that's a general idea that says if you have a complicated distribution, you can often approximate it by a mixture of simpler distributions. And we're going to apply that idea, except not in one dimension that you see here, but in five-dimensional space. So we have, again, this complicated distribution of 5-dimensional points. Each point is an ellipse. And we think about that as a distribution. And we're going to approximate it by a mixture of simpler distributions. And when you have that distribution, the picture on the bottom left here is a way that says, imagine that there's a mechanism. The mechanism tends to produce ellipses of a certain kind and shape. And a pattern takes some of those different kinds of ellipses. And so if we can build such a model, and we can back out at the end and say, here's a matrix. Does this look like other matrices from pattern I? And I'll show you some results to give you an idea of what we're doing. Here's a summary of what I just tried to talk through, the two approaches. It turns out they differ in both interpretation. The discriminative does a great job classifying, as you'll see in a minute, but it's based only on this kernel measure, and you don't actually know what features it's using to make the distinction. So that's not wonderful. The generative gives you a likelihood type measure, and so can be a little bit more useful in that framework. Computationally, they have actually different strengths and weaknesses. The discriminative takes a very long time to learn, but once it learns, you can classify, in a minute or less, in seconds, basically. The generative model is easier to learn. It only requires one mechanism at a time, but to actually compute the likelihood, the approach we're working on new approaches, requires fairly detailed computation. So I have 2 or 3 minutes left. Let me try and talk to you about the results. So I have some data that we got when we were collaborating with Michael Taylor, who has since passed away, sadly. But so these are impact patterns generated in his lab using swine blood from different either impact or expiration. They're kind of hard to see. The things you can see most visibly are actually the pins keeping the paper up. So that's not what we're interested in. There are little red stains. And you can see that though the top 2 are impact and the bottom 3 are expiration, they look somewhat alike. And so you can see why there's some ambiguity here. So what we did is apply the 2 approaches that I've talked about. For the discriminative approach, what we basically did is we split the data. 60% we used to train and build a discriminative model. And then we used the other 40% to test how well we do. And then we repeated that split, train, and then test 10 times to get more variability in average. And for the generative model, we only did it once because it's more computationally intense. We end up with a likelihood ratio comparing the 2 mechanisms. And I'll just point out a few things because time is really going quickly. What you can see at the bottom left is the discriminative model distinguishing between impact and expiration. You can see that it really does a very, very good job with a small number of misclassifications. The table above it, over here, shows you what happens if you just use locations or just use the shape of the ellipse or just use the angle of the ellipse. You can do well on any of those, but the bottom is what we really do, of course, which is use all of the data. The right-hand side shows you the likely ratios. In one of the earlier talks today, there was some talk about calibration. You can see these are not terribly well calibrated because the likely ratios, and these are log likely ratios, are enormous. But you can see they generally do a good job of distinguishing impact patterns from expiration patterns. And where they have trouble are where there are a smaller number of stains. And so last slide I have is this one, which shows you if you're computing likelihoods, the top 2 pictures are both impact, but the top one says, and there aren't many stains there, it's not all that likely to be impact. The bottom one, it's much more confident it is impact. And then you can see on the bottom, expiration. Again, the number of stains matters a lot. If you don't have a lot of information, you can't distinguish. And the last on the bottom right is an example of a pattern that was misclassified as an expiration. It was really an impact, but it was an expiration. So this is work in progress, and wanted to share how we're reducing the data and how we're feeding it into statistical analysis.